Welcome to an energetic exploration where we're going to treat organic chemistry not as some dry list of facts, but as a dynamic, real-time rulebook of molecular survival. Today, in this explainer, we're zooming in on how the hidden architecture of a molecule literally dictates its entire future. It's going to be a fun ride. Okay, so our roadmap for today covers three main areas. We're going to look at substitution versus elimination mechanisms, then dive into benzene's electrophilic substitution, and finally wrap up with acidity and basicity trends. Let's get into it.
Starting with Part 1, Substitution versus Elimination Mechanisms, or what I like to call environmental tugs of war. So, let's start by looking at the fascinating behavior of halogenoalkanes. You know, these molecules essentially sit at a chemical crossroads, and the path they end up taking, well, it depends entirely on two things: their internal build and their external environment.
It's actually wild how a molecule's inherent structure forces it down completely different energetic pathways. Take a primary halogenoalkane. It opts for a swift, single-step pathway. We call this an SN2 mechanism, and it zips right through a transition state. But if you bulk that molecule up into a tertiary halogenoalkane, it just can't make that simple, single step anymore. It's physically forced into a complex, multi-step SN1 journey, relying on the formation of a stable carbocation intermediate just to reach its final form. So right off the bat, we see that structure dictates the journey.
And this brilliantly illustrates the whole if-then algorithm of chemistry. Let's factor in the external environment for a second. If you take these halogenoalkanes and expose them to aqueous sodium hydroxide under reflux, they undergo nucleophilic substitution. But, and here's the crazy twist, simply swapping out that aqueous environment for a hot ethanolic sodium hydroxide solution shifts the entire energetic pathway. The substitution is abandoned entirely, and we get an elimination reaction instead. This produces a brand new alkene alongside water and a halide ion. The solvent literally flips a switch on the molecule's destiny.
Moving right along, let's get into Section 2, benzene's electrophilic substitution, the stubborn ring.
Benzene is absolutely famous in the chemistry world for being this highly stable, exceptionally stubborn molecule. Which really begs the question, right? Why does it outright refuse to undergo the standard addition reactions that we see so easily in other organic compounds? Like, why won't it just add new atoms to its structure?
Well, the answer lies in its incredible architecture. Benzene is built as a planar, perfectly symmetrical ring. But its real armor is the delocalized pi electron cloud. Because this electron cloud is positioned both above and below the carbon ring framework, it provides just an immense amount of stability. It's essentially a chemical shield, locking the molecule's structure tightly in place.
So the absolutely crucial takeaway here is that benzene does not add new atoms. It swaps them out. It heavily favors what we call electrophilic substitution. That dense, hovering cloud of pi electrons, it acts like a powerful magnet. It actively attracts electrophiles, pulling them in to substitute an existing atom, rather than breaking that beautiful, highly stable ring open for an addition.
But here's the catch. You can't just throw any old chemical at benzene and expect a reaction. No way. To actually breach its defenses, say for a nitration reaction, you have to synthesize something highly aggressive. By mixing concentrated nitric and sulfuric acids, you generate a highly active nitronium ion along with bisulfite and hydronium ions. And it's really only with a battering ram as strong as that nitronium ion that you can actually force a substitution on the benzene ring.
All right, that brings us to our third and final section, acidity and basicity trends, the power of a lone pair. Let's uncover how the subtle placement of a single, tiny pair of electrons can drastically tip the scales of chemical behavior. We can map out these electronic trends from our source material to see exactly why certain molecules act as acids and others act as bases. Okay, let's start with acidity. By comparing phenol to ethanol side by side, a massive difference emerges. Phenol displays significantly higher acidity. Now, why is that? It's because the lone pair on its oxygen atom overlaps directly with that delocalized aromatic ring we were just talking about. This overlap stabilizes the resulting phenoxide ion. Ethanol, on the other hand, simply doesn't have an aromatic ring to offer this kind of stabilization, leaving its acidity much, much lower. Once again, structure completely dictates strength.
Flipping to the other side of the coin, let's look at basicity in nitrogen compounds. Basically, basicity is simply a measure of availability. It depends entirely on how available a lone pair on a nitrogen atom is to literally reach out and accept a passing proton. The more available the lone pair, the stronger the base. Make sense? Let's take ethylamine, for example. It acts as a stronger base than ammonia, and that's because of the electron-donating inductive effect of its alkyl group. Think of that alkyl group like a chemical cheerleader, pushing electrons toward the nitrogen, which makes that lone pair highly available. Conversely, phenylamine is a weaker base. Why? Well, its nitrogen lone pair is actually drawn away, delocalizing directly into that stubborn benzene ring system we discussed earlier. The ring hoards the electrons, making them completely unavailable to catch a passing proton.
All of this leaves us with a really fascinating realization about the microscopic rules governing our universe. From an external environment forcing an elimination reaction, to a benzene ring acting as an impenetrable shield, to a single lone pair of electrons, to finding whether something is an acid or a base, structure truly is destiny. If these invisible tugs of war are happening right now at the molecular level, what other hidden forces do you think are dictating the physical world around us? It's definitely something to think about.